Hey guys, so on our as we look a little more into interference, we get into what we call two-source interference. When we talked about beats, we did talk about two waves interfering that happen to be at frequencies that were pretty close. Here we're going to talk about something a little bit different. We're going to talk about interference of two sources that are what we call coherent. What that means is that they actually play or emit the same exact frequency wave. And when they emit them in phase. We'll sort of formalize that in a minute. But if we have two, let's say we had two speakers like this, and they played a single frequency. Well, what we could see is, well, not see, but what would happen is that the waves from each source, if we could see them, I guess, would look something like that. Those are wave fronts, right? So we can actually observe here the wavelength of each wave, right? There to there is wavelength. And notice that each wave puts out each source, puts out a wave of the same wavelength, right? And notice that, it looks like at the same instant, a peak came out of both ones. So we say that they leave the sources, the waves leave each source in phase, all right? So the question is, if you wanted to hear something extra loud, where could you sit, all right? Well, you could sit something like right here, or right here, or even right here. Because here we have peak and peak interfering. Right? That makes a bigger peak. If these are sounds, that makes a louder sound. Here we have trough and trough, which makes a bigger trough, which is louder sound. Okay? You could also sit here, or here, or, well, that looks like there are lots of places. You could sit really anywhere along this line, anywhere along this line, anywhere along this line. And there are lots of other places also. Okay? So anywhere where we would get constructive interference, you hear a louder sound. There are places where you could sit and hear nothing. And those are places like right here. Because right there we get a peak and a trough. Right? Here's the peak of one, and this is the trough, right, between the two peaks of the other. So right there, those two waves would interfere destructive. Destructive. Here I should put constructive. All right, so there we hear nothing, and also here, and also here, and, well, really anywhere along this line. Anywhere along here, we have peaks lining up with troughs, right? Anywhere along here, we have peaks, lining up with troughs. Anywhere it looks like along here, we have peaks lining up with troughs. Now, the reason that, you can't go to SPAC and hear nothing if you sit anywhere, because the sound is not only coming from the two sources, that, if there were two speakers, but it's coming from, it's echoing off of trees and other things and, parts of the amphitheater. And so there aren't really just two sources. All those reflections off of walls and trees and people and buildings act like another source. Right? But if there really were only two sources in a totally acoustically insulated environment, you really could move from one place to another and hear something loud and hear nothing at all. Okay? So that's sort of the basis of what we call two-source interference. Now, what we will typically do is not so much do these with sound, although, well, yeah, typically we do these with light, all right? And we call this double slit or two slit interference. And this setup you see here is a really a very zoomed in look at literally. We have slides that I'll show you, like a slide that used to go on a slide projector, and it's all black except you see, well, I'll do the kind of negative of it. It's all black, but there are literally two tiny little slits in it right next to each other. And you can shine a laser through those. All right, and each of those slits, fire out. All right, let's see, what is this? Yep, blah, blah, blah. What's that? So yeah, each one of these, here's one of the, here's one of these slits right there, and here's the other one right there. So we're sort of looking as like a top view down on these slits. Okay. Sorry. Okay. So if we take a source of light, like perhaps a laser, and we shine it at these slits from somewhere way back there, the light hits these slits, and the nice thing is, just like we played those two speakers where the sounds left the speakers in phase, here, if a peak gets to here and here at the same time, it means that the light will leave these two slits in phase. All right? Now, here's our assumptions that we make here, is that the light source is what we call monochromatic. One color, right? Single wavelength or frequency. Sure. Yep. And coherent, we mean really leaves in phase. Okay? So there's the light that comes from one source. Here's the light that comes from another source. And what we do is we put a screen over here. So instead of you moving from one place to another where you might hear different things, we put a screen there so you can see different things. All right? Now, each of these waves, maybe we call these waves like wave 1, and the other one's wave 2. Each of those waves travels a certain distance to get to our screen. Yeah? So there's like a distance that wave 1 travels to get to that point, to this, to get to this specific point right here on the screen. Wave 1 has to travel some distance by, represented by that dotted line. Wave 2 has to travel a certain distance represented by that dotted line. And what we can ideally see is that in this case, the two distances that the waves travel are the same. And if that happens, well, they started here and here in phase. They traveled the same exact distance to get to here. That means they better arrive there in phase. Okay? It's kind of like saying if two of us have the same exact stride length, and we both, let's say we say ready, set, go, and we both start, walking and step with our right foot. Well, if we each travel the same exact distance, and we both have the same exact stride length, well, we're going to get to the same place, on the same step. Make sense? All right. So if two waves arrive there in phase, that means they'll interfere constructively. All right? And if this is light, you got to think about what that means. Now, we'll quantify this distance. We're going to call it D. The AP might call it something else, but that's okay. They might call it X or L or something like that. But here's a case where a wave, to get to this specific point, right, on the screen, wave 1 travels whatever the length of that line is. Wave 2 travels a different distance. That's farther. Agreed? The length of this line here is farther than longer than the length of this line. So they travel different distances. And what we can do is say, well, here's this triangle here. And this part of it right here represents the extra distance that wave 2 traveled. Now, we're making an assumption here. What we're actually assuming, let's see if these assumptions pop up. Oh yeah, so we call this little extra distance, we call it delta. All right, capital delta, lowercase delta. All right, so since it's a little tiny difference in distance, on the order of, billionths of a meter or so, we call it a little difference, or we call it lowercase delta. All right, but notice, right, anywhere along that line, even though the path lengths, what we call the path lengths, this is a path length, this is a different path length, even though those path lengths are different, everywhere along this line right here, we see that waves are interfering constructively. And why is that? Well, it's exactly because, what do you notice here about our little delta? How far is it? It's exactly one wavelength. Oh yeah, okay, so this you gotta read this thing real careful. How many wavelengths are there from source 1? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 so far. How many from source 2? There's 1, 2, 3, 4, 5, 6, 7, 8, 9 so far. Well, to get to that point on the screen, watch this. There's 1 extra, so 10 from wave 1. And to get to that point, notice 2 extra from source 2. So that means to get to this point, there are 10 waves from wave 1, 10 wavelengths from source 1, and 11 wavelengths from source 2. So that means that our path length difference delta, here it is equal to exactly 1 wavelength. Okay? So we'll say that again. The reason that we get here and interfere constructively is that the difference in the path length from each source is equal to 1 wavelength. Now look at this case. Here's a case where if we look, we look at a place like this, there's a length from source 1, there's a length from source 2, there's a path length difference, and now our little tiny delta, if we look at anything along this line here, all we see is that waves are interfering destructively, right? So we get right here a peak and a trough, right here a trough and a peak, right here a peak and a trough. Anywhere on there are peaks and troughs interfering. That's destructive interference. And that happens because the path length difference, here's our little tiny delta right here, is equal to, well, look, there's our 9, 10 for source 1. Here's our 9, 10, well, there would be 11. So the difference in path lengths is half a wavelength. So how these waves interfere when they get to the screen, here's the screen. How those waves interfere depends entirely on what the difference in the length of their path to get there is. All right, what does this look like? Well, if we get constructive interference, the light, you see bright light. If you get destructive interference, you don't see anything. If you get constructive interference, you see bright light. If you get destructive interference, you don't see anything. And that pattern repeats itself and gets a little dimmer. Definitely gets dimmer as you get wider and wider, but it keeps happening. Okay, now, we call this angle, we're going to refer to that angle between what we call the, hang on, sorry folks, let's just see what pops in here and how far we're supposed to go. Not sure why. Well, we call that angle theta, and that angle is between what we call the central maximum and the, we call this the first order maximum. So there's an angle that we can make with this triangle. We call this angle theta. Now, even though these two lines here, this one and this one, are not parallel, we sort of assume that they are because this distance d is so small compared to this distance d. I mean, this is going to be on the order of some meters, and this is going to be on the order of, maybe 10 to the negative fourth meters. All right, so these two lines, this one here and this one here, we can assume are just about parallel. All right, and so what we can say is there's an angle here that we call theta, and that same angle shows up right there. All right, we're really saying that this triangle and this triangle are similar. Okay, so there's our, what we call the distance between the slits, lowercase d. Here's this angle between the, that exists between the central maximum and the first order maximum. Whoops. Come on. And we're going to relate those. I think we'll do it in the next slide. So really, this pattern just like I said, keeps repeating itself. There's the central max, there's the first order, here's a second order maximum, and a third order maximum, and so on and so on. All right? Whenever we see a maximum, it means that, like we said, our path length difference, well here, our path length, our path length difference, get out of there, fine, was equal to 1 wavelength. Well, here our path length difference is nothing. Here our path length difference is also 1 wavelength. Here our path length difference is 2 wavelengths. Our path length difference is 2 wavelengths. And for the third order maximum, our path length difference is 3 wavelengths. And so on and so on. Here, for these minima, I don't know what you call these, a first order minimum, I don't know. So here's a minimum. Here that means that the path length difference is, 1 half wavelength. Same thing here. Oops, I'll just call it lambda over 2. Here the path length difference is, 3 half wavelengths. And here it's 5 half wavelengths. And so on and so on. 3 halves, 5 halves. Okay? So in general, when do you see a maximum? Right? In general, you see a maximum if this is a certain number, if path length difference, what do you call it there, delta, is an integer number of wavelengths. And this triangle, because we put, because we put a right, because we put, we can say this is a right angle right there. Don't shoot you again. Good. There's a right angle right there. We can relate d and delta and theta like that. That delta is d sine theta. Makes sense? And here's the big boy. That's the one you use all the time for these. And lambda is d sine theta. That's the criteria for a maximum. Maximum means bright or loud. It means constructive interference. Okay? Okay. Yeah, forget about that stuff. Now, it works for 2 slits. Okay? What's odd is that it actually works for a single slit. Right? You put 1 slit in there, and the way that we talk about this is that even if you take 1 slit, it's kind of like, it's not like there's really one source in there. So we take that slit, we divide it in half, and we say that in each half of the slit sort of acts like a source, and you can get an interference pattern that looks like this from a single slit. And notice that here's our plain old double slit thing where we said, sure, there's central max and next one and next one and next one and next one and next one. But that pattern has to fit into this general envelope. Notice this thing here, that same pattern is right here. And then from the page before, our double slit pattern, that there's no justification why it shouldn't be bright, 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 why they shouldn't all be the same brightness, right? Well, they're not, because they have to fit into this general envelope. Okay? And notice what happens. With 3 slits, things just get a little sharper. With 4 slits, 5 slits, they just get a little sharper. And we'll eventually deal with things called diffraction gratings. I'll show you one of those where the more slits you have, and a diffraction grating is just a ton of slits, the peaks just get sharper and sharper and sharper. And so instead of being like, you know, dim and bright and dim and bright, it just goes from nothing, dot, nothing, dot, nothing, dot. All right, but I'll show you both sometime soon. Okay? Okay, this is the second question you have, but it's the more straightforward one, or the more conceptual one, I guess, so good thing to answer first. So Young is this guy who really rocked and rolled with this double slit stuff. So in a Young double slit experiment, blah, 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 there's a separation. It's illuminated by that wavelength light. There's a screen that far away. None of those things are really important in this question, but it says, what's the difference in path lengths from each slit to the screen at the location of a third order bright fringe, right? So again, we have 2 slits, we have the screen, and we basically get like bright, dark, bright, dark, bright, dark, bright, right? And this is, let's see, so this is first, that's second, that's third. So here's the other first, and then bright, dark, and then the other second, dark, and the other third. So, I mean, for A, what's the path length difference to get to here? Well, that path length difference that we call delta is 3 wavelengths. There's no real math to do here at all. Okay? And B, what's the path length difference to go from the screen to the location of the third dark fringe away from the center? So here's the first, the second, the third dark fringe. So here's half a wavelength. There's 1, there's 1.5, there's 2, there's 2.5. So the path length difference is 5 half wavelengths. That's it. That's all there is to do here. All right. In a question like this, we actually get to use, use some of those relationships we just came up with. So, light is an electromagnetic wave, just like radio waves are. Just the wavelengths are very different. All right, but here's 2 radio antennas, like our 2 light sources, separated by 300 meters. Blah blah blah. Same wavelength. Yeah. Okay. The second maximum, and I don't know if they mean the second order maximum, or if they mean sort of like constructive, destructive, constructive. That that's the second maximum. Let's assume that it's the second order. Okay, what's the wavelength? All right, so if at 400 meters away from, the midpoint between them, that's 400 meters, if that's the position of the second order maximum, let's find that wavelength. So, what we're going to start with is we're going to say that n lambda is d sine theta, where for us, n is 2. Right? We're saying that this is really saying that n lambda is delta. The path length difference has to be an integer number of wavelengths. Well, how many wavelengths in this case? If it's a second order maximum, it's 2 wavelengths. Okay, so we start with n lambda is d sine theta. We're looking for lambda. Well, we need to know theta, right? Because lambda is going to be d sine theta for us, in this case, over 2. Now, theta, we just use some trigonometry here and say that, in this case, the tangent of theta is 400 over 1,000. So that angle is 21.8. And then we say that lambda is d 300 meters times the sine of 21.8 degrees over 2. 300 sine answer divided by, well, let's see, answer divided by 2. So I get that lambda is 55.7 meters. That's a big wavelength, right? That's one wave is 55 meters long. Well, that is, radio waves are big doggies. Okay? So this is two-source interference, folks. Okay? Here's your bread and butter. All right, understanding the idea of there being different lengths of paths from one source, from each source to a place where each of those sources are observed. Here's a place where each of those sources is observed. The fact that these paths are different lengths says that they can interfere in different ways based on what that difference in path length is. Okay? Tricky stuff for sure. A good demo coming sometime soon. All right, folks. Have a good weekend. Or I'll see you soon. Sorry.